Hello everyone. Today we'll be showing you our design for chess AI, which we call the one-shot chess. So in general, our approach combines the best of supervised learning as well as reinforcement learning. The term one-shot is actually derived from a concept in computer vision called single-shot detection, which allows you to detect multiple things at once. So we aim to make our design slightly more efficient. We hope that you enjoy the presentation. Why do we choose to explore chess when there's already the popular Stockfish as well as the famous AlphaZero? This is because these two agents require lots and lots of training, and it's very difficult to use because of the amount of resources they use. For example, AlphaZero needs 5,000 TPUs to train an agent for this, so this is not accessible to everyone, in particular students and hobbyists. Therefore, they will be our main target audience for this project. With the target audience in mind, we laid out 4 properties of our solution. So it must require minimal amount of compute resources, which is quite obvious. The next is the availability of data. Well, because this is one of the only ways that we know of to accelerate the training process. Next, it must be a lightweight model because typically this would be deployed in mobile devices, as well as we know that deep neural networks take a long time to train. Finally, it can be iteratively improved, which means that the minimum viable product can be easily reached, and it can be gradually improved with subsequent training. There are 3 underlying processes that we use to train our agent. So for the first step it does is to learn rules. This can be easily done with supervised learning since it's just telling what the model can or cannot do. The next step is to copy strategies, which is slightly more complicated because it has to try to approximate what the agents in the dataset tried to do. With this tool, this is just a supervised learning problem, and it simply emulates what other agents have done. To improve upon this, we use Monte Carlo tree search to improve its strategy. Let's look into what Monte Carlo tree search is. Monte Carlo tree search is actually a combination of 2 things: the classical tree search as well as Monte Carlo simulation, which is commonly used in computational finance. What it does is to conduct a series of random walks from the start state to terminal state, and that should give you some output. So for chess, it would be win or lose or draw, and that is then used to approximate how good the root node is. So with combining this tool gives you the Monte Carlo tree search, which comprise of 4 components: selection, which is selecting which node to expand, and then once it does, it expands by taking an action. To evaluate how good an action is, it simulates it with Monte Carlo simulation. And it should give you some result back. And with that result, you backpropagate the results all the way to the ancestors. The policy network is used to approximate the policy function. And it has 2 outputs, source and target. Source is the probability of which piece to move, and target is where to move it to. So there are several components in the neural network architecture. So feature block and sandwich blocks are the same architecture, and they're used to extract features. So feature block's output is passed to source policy, which determines the source. Sandwich block is in between the feature block and the target block. So the output of the sandwich block is given to the target block. Piecing everything together, we get the following pipeline. Because the chess game dataset is in text format, we convert it into matrix and tensors, which gives us our source and target policy data. This is then fed into the policy network training to give us a policy model. Now, we use the Monte Carlo tree search to generate data, using the policy model as a heuristic. So with this data generation, we get more source and target policy, which then we improve upon the policy model. And we can do this iteratively until we get our final policy model.
So now we know how one-shot chess should actually work. Now the question is, does it actually work? The answer to that is, it actually kind of does. To benchmark our model, we use Stockfish, which is a state-of-the-art chess engine. By changing its ELO rating, which is a popular metric for measuring chess performance, we are able to determine how strong our AI actually is. The higher the ELO rating, the more difficult the opponent is. We can see 2 graphs here, depicting the expected outcomes of matches against Stockfish with ELO ratings of 800 and 2000 respectively. An expected outcome of 1 means we, the player, are more likely to win the match, and 0 means the opponent is more likely to win the match, which is in this case, Stockfish. A value of 0.5 indicates a draw is imminent. First, let's look at the graph with the Stockfish with ELO rating 800. The uniform random policy, represented by the yellow line, loses ground quite quickly. This is to be expected because you wouldn't expect someone making random moves to win a chess game very well, or to perform very well, for that matter. As expected, when Stockfish plays against itself with the same ELO rating, we can see that it is very likely that it will have a draw in the game. This is to be expected when you have an opponent of similar caliber, or in this case the exact same caliber, you expect them to draw. Now, when you look at one-shot chess versus Stockfish, you can see something different here. We have two models, one which is trained with Monte Carlo tree search, and one that is trained without Monte Carlo tree search. The one trained without Monte Carlo tree search is shown in green. As you can see, at the beginning it performs slightly better than the opponent, Stockfish with ELO rating 800, but then after around move 20 it starts to taper off and then it eventually loses the game. This isn't the same for one-shot trained with Monte Carlo tree search, however. When comparing it to our previous model, without training with Monte Carlo tree search, it follows the same sort of pattern, but then around round 40, it starts making a comeback rather than tapering off and losing. During this comeback, it is able to either draw, or maybe even win against Stockfish. Now, if we take a look at the games against Stockfish with an ELO rating of 2000, things change. Again, the uniform random policy loses ground very quickly. When our player is Stockfish with an ELO of 800, it also immediately starts losing ground. Surprisingly though, one-shot with Monte Carlo tree search training performs worse than one-shot without Monte Carlo tree search training. We're not quite sure why, but it is possible that Stockfish is exploiting an inherent flaw in our model with Monte Carlo tree search. Finally, let's take a look at what happens when we have one-shot with Monte Carlo tree search play against many difficulties of Stockfish. Generally, one-shot performs very well in the first few moves. Even when playing against Stockfish with ELO 3000, which is higher than every human in the world, one-shot doesn't start losing immediately. That's amazing! But one-shot does start losing this lead after the first few moves. This demonstrates the lack of data on the later game states when compared to beginning states. However, one-shot does win one game and almost draws another, against Stockfish with ELO 800 and 1100 respectively. From this data, we can extrapolate that one-shot has an expected ELO of 1100. Considering that the average chess player, not beginner, has an expected ELO 1500, that's not terribly bad.
Hi, I'm Steven, and I will be demoing the chess AI. I'm playing as white, and the AI is playing as black. I've already played my first move, and on the left we have some console output. These two matrices represent the outputs of the policy network, where the source probability represents the source square, and the target probability represents the target square. Here I also have the expectation, which is Stockfish's evaluation of the expected outcome of the position. 0 represents a loss for the AI, and 1 represents a win. Now I'm going to be playing some moves. This is known as the Queen's Gambit. If you have not seen the show, The Queen's Gambit on Netflix, I would highly recommend that you do. So this is a common middle game position in the Queen's Gambit, which is played at the top level, and the AI has managed to derive these theoretically strong moves. Stockfish says that white is slightly winning, but this position is known to be fairly equal with both sides having fighting chances. In this game, I'm going to deviate from theory and go for some cheap tricks to get an early checkmate. The moves that I'm making are suboptimal, and the Stockfish evaluation reflects this. It already says that the AI will win this game 100% of the time, given reasonable play. However, due to lack of self-learning, plus the fact that the AI has likely never encountered these suboptimal moves before, it doesn't know how to play against it, which is how I'm able to achieve checkmate in 6 moves.
Throughout the creation of this, there were some troubles that we did run into. The model underfits, and this is shown by poor late game performance. We didn't have enough data to perform well later in the game. This was supposed to be remedied by the Monte Carlo tree search, but we ran into some problems with that as well. It wasn't very well optimized, and also we didn't have as much compute power as other projects have done in the past. For example, AlphaZero uses 5,000 TPUs for its training over the course of many hours, We used a single CPU core for the Monte Carlo tree search training, which is significantly less than the 5,000 TPUs that Google used for AlphaZero. Thanks for listening. We hope you enjoyed our little presentation about our little project. If you want to learn more, visit our GitHub page in the description below. If you liked this video, hit that like button. And if you really liked it, maybe even subscribe. Thanks again, and bye for now.